Imagine a world without a digital blueprint, a world where every app, every website, every smart device ran on pure guesswork. Sounds chaotic, right? Well, the digital systems that power our lives, from your online banking to your favorite streaming service, they are far from guesswork. They are meticulously designed, piece by piece, data point by data point. The digital world doesn't run on magic, it runs on systems. And learning to design them starts here. Welcome back to the Deep Dive, where we take complex topics and distill them into essential knowledge and some surprising insights. Today, we're plunging into the core of how those digital systems are built. We're focusing on structuring system data requirements. This comes straight from Chapter 8 of Valanchik and George's Modern Systems Analysis and Design. Our mission for you, our curious learner, is to, well, demystify how we build the bedrock of any information system. It's data. We'll uncover the often underestimated importance of something called business rules, explore how we visualize data at different levels of detail, and give you the practical takeaways you need to navigate this critical field. This deep dive is especially tailored for those of you in BCIS 3389 at Tarleton State University's Dr. Sampak College of Business. It provides skills vital for really any business professional navigating the digital landscape. Before we dive into the fascinating world of data architecture, if you're finding these deep dives valuable for, positioning yourself for a bright future, do us a favor. Hit that like button, subscribe, and share this deep dive with a friend who's curious about how the digital world really works. Your engagement helps us bring more insightful content to you, and as always, you'll find additional resources and links in the description. Go check those out to go even deeper.
Okay, so today we're going on a journey. We're starting from this abstract concept of really understanding what a business needs, all the way to the concrete blueprint of a functional database. We'll explore why clearly defining your data requirements is not just important, but absolutely paramount. It often prevents colossal project failures, honestly. We'll dissect the different levels of abstraction in data modeling and show you how crucial business rules are, and not just for data quality, but for the very success and, well, longevity of any information system. Ultimately, it's about building a consistent shared language for your data, making sure your systems are not just technically functional, but truly reflect and support the deepest organizational needs and strategies.
Okay, let's unpack this. Imagine you've just poured immense resources into a major software project. Big celebrations, high fives all around, right? And then, almost immediately, a stack of change requests lands on your desk. And not just little tweaks, but fundamental shifts. It feels like a successful launch, but the aftermath, it tells a drastically different story. It's kind of like building a beautiful house, looks perfect, but after the family moves in, they realize, uh-oh, we need 3 more bedrooms, a different kitchen layout, maybe an extra bathroom. The foundation's solid, the structure's sound, but the fundamental needs weren't quite met from the start. What went wrong there?
Yeah, it's astonishing how often that happens. Major software projects, despite all the fanfare, they just hit this brick wall of reasonable changes almost right after launch. What's truly surprising and often overlooked is that this isn't usually a failure of coding or project management. It's a fundamental misunderstanding of what the business actually needed in the first place. The Business Rules Journal points this out perfectly. If you end up with a huge stack of reasonable changes, it signals a critical failure in the very first step, the requirements analysis. We're talking about something so basic, yet it's like the hidden iceberg that sinks countless projects. It leads to these silent costs you rarely see on a balance sheet, but boy, you feel them everywhere. Organizations often try to, well, fight the symptoms of these problems with increasingly sophisticated change management processes.
Right, just patching things up.
Exactly. It's like patching a leaky roof again and again instead of finding out why the foundation is cracking.
Yeah.
The real issue, the root cause, is poor requirements analysis early on. It's not just about managing changes, it's about proactively defining things so accurately that you minimize those unforeseen changes by getting it right the first time, or as close as possible. Let me give you a concrete example. Imagine a large e-commerce company decides to revamp its customer loyalty program. They build this brilliant new system, but in the rush, they fail to meticulously define how points are accrued or redeemed, or how customer tiers are determined based on purchase history across, say, different channels.
Okay.
The system launches, and bam. Suddenly, loyal customers are complaining about incorrect point balances. Or the marketing team can't segment customers accurately for targeted offers. The system is functional. I mean, it technically works, but it doesn't align with the actual nuanced business rules of the loyalty program.
So it's not really doing the job it was meant to do.
Yeah.
Precisely. The result, immediate demands for extensive changes, costly redevelopment, and a significant blow to customer trust. This isn't just a technical glitch, it's a profound business strain. Poorly defined data requirements directly lead to massive cost overruns. And for those in BCIS 3389, that's a direct hit to basic economic models, what we call KO1.
Right.
It results in misaligned systems that don't truly support organizational goals, failing to apply basic organizational models, KO2. And ultimately, it means wasted development efforts. Not just money, but the invaluable time and human resources of skilled people who have to go back to the drawing board.
Ugh.
This is exactly why early clarity, especially when it comes to the data that underpins absolutely everything, is so incredibly vital for project success and, frankly, organizational efficiency. That makes perfect sense. It sounds like organizations are often playing whack-a-mole with symptoms, not addressing the core issue. But this whole idea of getting it right the first time, isn't that almost an idealistic goal in a rapidly changing business environment? I mean, are there times when a project should anticipate a high volume of changes? How do you differentiate between, avoidable errors and just necessary adaptations?
That's a really crucial distinction. And you're right, no system is ever truly finished in a dynamic business world. Change is constant. The goal isn't necessarily zero changes. It's more about minimizing unforeseen and fundamental changes that really indicate a failure in that initial understanding. We differentiate between evolutionary changes, those are expected as the business adapts, and foundational changes, which point to a flawed initial blueprint. The answer lies in requirements analysis. This is the systematic, rigorous process of determining these needs. It's about digging deep, asking the right questions, engaging all stakeholders, and truly understanding the business landscape before design and development even really begin. It's an investment in foresight. Within this broader process of requirements analysis, data modeling is absolutely paramount, foundational. Think of it as creating a detailed, logical representation of all the fundamental things your organization cares about. We call these entities. And how they relate to each other, those are associations. And all the individual pieces of information or data elements that describe them. Imagine a huge, complex company like, say, Amazon. Their data model would have to encompass everything from customer to product to order to warehouse location, and how each of those pieces of information connects. The goal of data modeling is to capture the overall structure of organizational data unambiguously and in logical terms. This means we're describing the data independently of how it might be stored in any particular database technology. We're focusing on the business truth of the data first.
Got it.
And this deep dive is central to BCIS 3389's focus on the systematic analysis, design, and implementation of software systems. It emphasizes skills used in the first 4 stages of the system development lifecycle. It ensures that basic systems concepts, KO3, are applied effectively right from the outset, providing a robust, adaptable framework for understanding and building information systems that actually serve their purpose.
So if we're building this robust framework, before we can even think about database tables and specific structures, we need to understand the fundamental things our business cares about. What do we call these essential building blocks? And how do we even go about identifying them? It feels like a sculptor looking at a block of marble and envisioning the final form you need to understand the essence, the core elements, before you start chipping away at the details.
Exactly right. And this is where conceptual data models truly shine. They are the most abstract type of data model. They give you that high-level bird's-eye view of those core business concepts. Importantly, they are entirely platform independent. This means they define what data is important to the business, not how it will ultimately be stored or implemented in a specific database. It's about the pure, unadulterated business, meaning free from all the technical jargon. We use the term business concept here to emphasize it represents something important to the business, not necessarily a database table or a programming class just yet. These core business concepts are remarkably stable over time. Technology changes fast, right? But the fundamental things a business manages tend to endure.
That's a good point.
A conceptual data model focuses on these concepts, and the most basic ones. They're often identifiable as the nouns in the business's vocabulary. For instance, a business concept could be a person, like a passenger in an airline system, or a thing like an aircraft or a shopping cart. It could be a place like an airport or a store location, or even an abstract entity such as a flight or maybe a contract. These are the fundamental atoms of your business information. Now let's take a term that seems simple but often trips up entire projects: customer.
Oh, yeah, I can see that being tricky.
Right. Think about it. To a billing department, a customer might be someone who currently owes money or has an active payment plan. To a salesperson, a customer could be a prospective buyer who hasn't bought anything yet, but they're actively nurturing them.
Different perspectives.
Totally different. Does a customer have to be a person? Or can another company, a B2B client, be a customer? Is someone who bought something years ago but has no active account still a customer? Is there a difference between active and inactive, existing and prospective? Each department, each stakeholder might have a slightly different, perfectly valid interpretation based on their operational needs. This is where the true power of a conceptual model comes in. It forces everyone collectively to establish a single agreed-upon definition for terms like customer. It means gaining consensus from all stakeholders across the organization.
That sounds challenging.
Oh, it can be. You sit everyone down, you listen to their perspectives, and you work to find that common ground. But this consensus, often hard-won, significantly reduces ambiguity later on. Ambiguity is a huge source of project delays, costly rework, and frankly, internal friction.
Yeah, I bet.
It clarifies the fundamental language, the business vocabulary. It ensures everyone is literally on the same page from day one, not just conceptually, but structurally. Without this upfront work, you risk building a system where different parts are working with different customers. That leads to fragmented data, inconsistent reports, and ultimately, a system that doesn't serve anyone very well.
That clarity, that shared understanding, even for just one word like customer, seems incredibly fragile if you don't formalize it. So once we do agree on these core concepts and their precise definitions, how do we then go from these abstract ideas to something visual, something tangible everyone can work with? Because agreement can still just live in people's heads, right?
Yeah.
We need a visible blueprint.
You're absolutely right.
Yeah.
Agreement needs a common language, a visual representation. And this is exactly where entity relationship diagrams, or ERDs, come into play. An ERD is a graphical representation. It's essentially a data model that illustrates how domain-specific entities relate to each other within a system.
Okay, a picture of the data structure.
Exactly.
Oh.
It's a universal language for data structure, understood by both business folks and technical teams. And ERDs are absolutely crucial for several reasons. They're foundational for designing relational databases. Think of it as mapping out the blueprint before you pour the concrete.
Right.
They help establish a consistent vocabulary across the entire project team, cutting down on miscommunication. They illustrate complex business rules visually, making them much easier to grasp. They define the precise data requirements for an information system, detailing exactly what pieces of info need to be captured and how they connect. And ultimately, they plan how databases will store relational data efficiently and effectively. Now, there are several notation styles out there, Chen, UML, but crow's foot notation is really widely used. Yeah, because it's pretty intuitive and readable. It makes it accessible to both technical and non-technical stakeholders. If you looked at one, you'd see these little symbols at the end of the lines connecting entities. Like a straight line means one, and a three-pronged crow's foot symbol means many, often combined with a circle for 0 or maybe a hash mark for 1, indicating the minimum and maximum relationships allowed between things. When we look at the key conceptual components within an ERD, we start with entities. Like we discussed, these are those fundamental nouns identified earlier, the people, objects, concepts, events the business wants to track. In an ERD, entities are typically shown as rectangles or boxes. A useful technique for finding them is the noun technique. You review business specs, glossaries, business rules, and pull out all the relevant nouns. Helps ensure you don't miss anything critical.
Okay, find the nouns.
Then we have relationships. These are the verbs that describe how entities interact or are associated. They're shown by lines, connecting the entities, illustrating these bidirectional interactions. For example, a passenger books a flight, or a customer places an order. At this conceptual level, the ERD often includes only the most important concepts and their relationships. Sometimes we don't even specify all the individual attributes yet.
Attributes being the details about the entity.
Exactly, or the primary keys, the unique identifiers. We keep it high level at this stage, focusing on the big picture and the core connections. To help visualize this, let's imagine a simple, high-level conceptual ERD, like the one in the iLearn resource you might see. Picture a diagram with a rectangle labeled album, another labeled photo, another labeled tag. You'd see lines connecting album to photo and photo to tag.
Simple connections.
Right. These lines represent relationships. Maybe album contains photos and photo has tags. There are no details about specific IDs like album ID or data types like varchar 100 at this conceptual stage. It's pure business logic. It's a clean, clear overview of the information universe for that particular domain, easily understandable by anyone in the business. And for students in BCIS 3389, learning to interpret and implement these diagrams is a core skills outcome, SO3. It's a foundational step for using standard UNL diagrams at the database level, specifically the class diagram, KO4.
So it's a practical skill for bridging business understanding and technical implementation.
Absolutely essential.
Okay, so every organization, every system runs on rules. We get that. But in data modeling, you said these aren't just suggestions. They're the bedrock ensuring our data is reliable and useful. What exactly are these business rules? Are they just about saying no to bad data, or is there like a much deeper implication for how our systems actually function?
That's a critical point, and yeah, you've hit on a common misconception. Business rules are much more profound, much more pervasive than just simple data validation checks. They are the precise specifications that define the conditions, constraints, and relationships that guide how data is structured and used within an organization.
Okay, the operating manual for data.
Exactly. Think of them like that. They are absolutely crucial because they ensure that data models accurately reflect real-world operations, policies, standards. Without them, models can quickly become disorganized, inconsistent, and ultimately they fail to support effective decision-making. They can even lead to operational chaos. To put it another way, think of business rules like the DNA of your data.
Interesting analogy.
Yeah, they dictate its very form, its function, and critically how it interacts within the system and the broader organization. They establish the very essence of what the data represents and how it behaves. Without clear business rules, your data model is just a collection of boxes and lines. With them, it becomes a living, breathing representation of your business's operational logic. The benefits of explicitly defining and implementing these rules are immense, as OWOX BI highlights. They go way beyond just technical correctness. Firstly, they provide clear data definition. They ensure only relevant, necessary information is collected and stored.
Cuts down on clutter.
It's exactly. Focuses your data collection efforts, reduces storage costs. Secondly, they foster structured hierarchical relationships, building clear, consistent, logical connections between different data points. This is fundamental for understanding how information flows and is organized. Makes it easier to query, easier to report on. Thirdly, business rules lead to enhanced data security. They enforce access controls, validation measures. Like a rule might say only managers can view salary data, or a user must re-authenticate after X minutes of inactivity.
Important stuff.
Very. Safeguards sensitive info, ensures compliance. Fourthly, and maybe most importantly for operations, they result in higher data quality. By setting rules for allowed values, like age between 18 and 120, mandatory fields, every customer needs an email, referential integrity, an order must link to an existing customer. Business rules actively prevent errors, duplicates, and inconsistencies from creeping into your database.
Like data gatekeepers.
Precisely. Imagine a world where every entry is clean, consistent, correctly parked. That's the power of robust business rules. Finally, they enable customized operational alignment. They tailor the data model to precisely match the unique processes and priorities of your organization. This ensures the database accurately reflects genuine business needs and supports specific workflows, rather than imposing some generic, ill-fitting structure.
That's a truly comprehensive list of benefits. It really underscores how understanding and explicitly defining these rules isn't just technical. It directly prevents costly errors that tie straight into basic economic models, KO1, and it ensures the system truly supports the business's unique operations, applying this fundamental organizational and systems concepts, KO2 and KO3. It seems like without these rules, you might as well be building a house without a building code, just hoping it stands up. So given this importance, it sounds like business rules are far more nuanced than just simple validation. What are the different categories we should be thinking about? Because rule can mean so many things.
You're absolutely right. They are quite diverse. Understanding these categories helps us be much more systematic, more thorough in identifying them, documenting them, applying them. Business rules can generally be broken down into four main types, as detailed by OWOX, BI, and the ERIC Digital Library. The first type is definitions of business terms. These are foundational. They form the very vocabulary of your system. They define the precise meaning of terms used throughout the organization, ensuring everyone shares a common understanding. For example, in a library system, you need to define exactly what borrower means. Is it anyone who's ever borrowed? Only active members.
Right, like the customer example.
Exactly. What constitutes a library card? Just a physical card, an account ID. This clarity, though seemingly simple, is surprisingly powerful. It prevents ambiguity that could derail things later. It's the dictionary for your business. Next, we have facts relating terms to each other. These rules describe how different terms or entities are associated. They capture the inherent structure and relationships within the organization.
Connecting the nouns with verbs.
Good way to put it. For instance, a customer places an order. In our library example, a book will have an associated publisher. That's a factual relationship. Or a critical rule that directly impacts the data model design. The library will issue only one library card per borrower. These facts lay out the fundamental relationships, the backbone of your data model. The third category is constraints, also known as action assertions.
Okay, these sound more like the no rules.
They often are. These are the rules that restrict how data can be entered, modified, or deleted. They directly enforce business policies and ensure data integrity. They're designed to prevent actions that would violate organizational rules or create inconsistent states in the system. A classic example from the Business Rules Journal. A customer may not rent more than 3 cars at the same time, prevents an invalid business state. Or, in a library, a crucial rule might be one that denies checkout if fines are pending.
Makes sense.
These constraints are about maintaining control, ensuring compliance, preventing invalid states. They are the guardrails of your data. Finally, we have derivations. These rules explain how new information is created or calculated from existing data. They show how values or knowledge are inferred or determined based on other data points. For example, the rule, no apartment should be rented if there are complaints pending on the apartment.
Ah, so one thing affects another.
Exactly. This shows a derivation where the status of one entity complaints directly impacts the ability to create another entity a rental. Another example might be calculating a customer's loyalty status, gold, silver, bronze, based on their total purchase history over the last year. It's about how one piece of information can be used to generate or influence another, creating richer, more intelligent data.
It's remarkable how that detailed breakdown from just defining a term to a complex derivation that prevents an action essentially becomes the instruction manual for the system itself. It dictates not just what data it holds, but how it behaves. It really is the DNA, like you said, covering both structure and function.
Absolutely. And once these business rules are meticulously identified and documented, they aren't just abstract ideas floating around. They have to be actively enforced within the system to actually have an impact.
Right, they need teeth.
Exactly. This enforcement can happen at different layers of the system. It depends on the nature of the rule, how robust you need it to be, the system's architecture. We generally categorize them as either database-oriented rules or application-oriented rules. Database-oriented rules are implemented directly into the data model itself. This means using fundamental database features like constraints, triggers, or stored procedures. Their main job is to ensure data validity and integrity before it even hits the application layer. They are the robust first line of defense for your data.
Like a gatekeeper at the database store.
Precisely. For instance, a null constraint on a customer name field ensures every customer record must have a name. The database literally won't let you save a record without it. A unique constraint on library card number prevents duplicates. A great example of a powerful database-oriented rule is a trigger. Think of a trigger like an automated watchman for your data. If a new customer signs up, a trigger might automatically populate a welcome email sent field or even create their first loyalty points. It ensures consistent behavior without manual intervention from an application. These rules are enforced at the most fundamental level. They ensure data consistency regardless of which application talks to the database. In contrast, application-oriented rules live within the software interface the part users directly interact with. These rules guide user behavior during data entry or processing. They focus more on user experience, workflow, immediate feedback.
Like the pop-ups on a web form.
Exactly. Think of a message telling you your password needs a special character before you even try to submit it. While the database might ultimately enforce a password strength rule too, the application-oriented rule guides the user preemptively, makes the experience smoother, less frustrating. Another example might be dynamically hiding certain fields on a form based on a previous selection that's an application-level rule for UI flow. The Era Digital Library source gives a great real-world example of how these rules can work together in a library system. Consider the business rule. Once the registration is processed, a library card is issued, BRD4.
Okay, that needs to happen automatically.
Right? It's not just an application pop-up. It needs to be guaranteed. It can be elegantly implemented as a database procedure, maybe called Generate Library Card. This procedure would first handle inserting the borrower's details into the borrower table, and then, crucially, automatically insert a new record into the library card table. This same procedure could even include more complex logic, like assigning a library code based on the user's zip code. Maybe if the zip is 65804 or 65807, the code is SGF05, otherwise SGF10.
Ah, so derivations and constraints baked right into the database.
Exactly. It demonstrates how derivations like assigning the library code and constraints, ensuring a card is issued upon registration, are built directly into the database logic. Ensures critical policies are enforced at the most fundamental, robust level. This distinction is incredibly crucial for you as future systems analysts, as business professionals, because it dictates where and how you ensure data integrity and enforce policy most effectively. You need to consciously decide the best layer for each rule. You're balancing absolute data security, system performance, and optimal user experience.
It's a trade-off sometimes.
It can be. Some rules belong in the database for absolute, non-negotiable consistency. Others are better in the application for guiding users, immediate feedback, usability. This nuanced skill is vital for communicating system requirements effectively, W01. Ensures your designs are functional, technically sound, but also robust, user-friendly, and perfectly aligned with those big organizational objectives.
Okay, so we've defined our core business concepts. We've got the detailed rules governing them, dictating how data behaves. How do we take these high-level ideas, these abstract agreements, and progressively turn them into something a developer can actually build, line by line, table by table? It feels like moving from that architect's beautiful conceptual sketch to the detailed blueprints, and then finally to the actual construction plan, every brick, every beam, every pipe, every wire.
That's a perfect analogy. This is exactly where the three stages of data modeling, conceptual, logical, and physical come into play. It's a progressive journey. Each stage adds more detail, refines the structure, transforms the model closer to something implementable. It's a systematic way to refine our understanding and translate it into a concrete, executable technical solution. We start, as we've discussed, with the conceptual data model.
Right, the highest level.
Highest level, most abstract.
Yeah.
Entirely business-focused, technology-independent. It's primarily developed by business analysts trying to understand the core entities, their overarching relationships, without getting bogged down in technical details yet. It truly represents the what of the business information. Key players, key things, how they generally interact. Often lacks granular details like specific data types or unique identifiers.
Yeah.
Remember that simple ERD example we talked about? From learn, album, photo, tag as rectangles, simple lines connected them. No IDs, no data types mentioned yet.
Pure business logic.
Exactly. Its elegance is in its simplicity and clarity for business stakeholders. It's a shared vision for the data landscape. The next phase is the logical data model. And this is where we start getting very precise, but still without picking a specific database technology.
Okay, more detail, but still tech agnostic.
Right. Think of it like a detailed architectural drawing, every room, hallway, window laid out, but not specifying brick versus concrete walls or the brand of window. Here, we define the precise structure of data elements and their relationships. This includes all attributes, those specific pieces of info describing an entity. It includes primary keys for unique identification and foreign keys, the links showing how things relate across different data sets. These are all described in business-friendly language first, before any technical translation happens. A crucial step at this logical stage is applying normalization rules.
That sounds technical.
It does, but it's really about organizing your data efficiently and logically. It manages data integrity mainly by reducing redundancy. Imagine trying to find a book in a library where every book on, say, gardening has the publisher and author info repeated on every single shelf tag.
Inefficient.
Totally. Normalization is about streamlining that. You store publisher info once and link books to it. Ensures each piece of info is stored in only one place where it logically belongs. Significantly reduces chances of inconsistencies and errors. This is key for managing data quality, KO3. At this logical stage, those complex many-to-many relationships, like many students taking many courses, get broken down.
How do you do that?
Often by creating an associative entity, essentially a new thing, like a course enrollment entity, just to manage that relationship. And we get very specific about cardinality, using visual cues like crow's foot notation on our diagrams, which, again, looks like a little three-pronged symbol indicating many. We show exactly how many instances of one entity can relate to another. For example, a book can have 0 to many reservations, but each reservation can be tied to only one book. We specify that precisely. If you look at the logical ERD example from iLearn, you'd see rectangles now with lists of attributes inside, like albumate, title, release date for the album entity. You start seeing explicit connections between these IDs. Maybe even some basic data types mentioned if they help business analysis, but still no commitment to a specific database vendor. Finally, we arrive at the physical data model. This is the last stage, the actual design blueprint of a relational database ready for implementation.
Okay, this is where the specific tech comes in.
It is implementation technology specific. It defines exactly how data will be structured in a particular database management system, DBMS, Oracle, SQL Server, MySQL, Postgres, whatever it is. This model includes precise database-specific data types, varchar 2555 for text, INT for numbers, datetime for dates, specific table names, often pluralized like albums instead of album, column names. And it addresses non-functional requirements like performance optimization through indexing, managing concurrency, how multiple users access data simultaneously, implementing security protocols. At this stage, generic entity names become concrete table names. Abstract attribute names become specific column names, all translated into language compatible with the chosen database. Many-to-many relationships are now concretely implemented as new tables, often called junction or associative tables. If you refer to the physical ERD example from iLearn again, you'd see how ID fields now have specific types like int5. Title becomes varchar. And that many-to-many relationship between tag and photo is explicitly implemented as a new table. Tag photo, containing tag it and photo ID as foreign keys.
So that's a final blueprint that developers use.
Precisely. That's what a database administrator or developer would use to create the actual database structure.
So if I'm understanding this correctly, this progressive layering ensures we start with the big picture business needs, then systematically add the precise business logic, and then finally translate that into the technical specs for a specific database. It's a structured approach that minimizes surprises and ensures the final system truly reflects what the business requires, from the most abstract need down to the most granular technical detail. That's incredibly powerful for ensuring alignment.
Precisely. And in this journey, from abstract concept to deployable code, the Unified Modeling Language, or UML, plays a very significant role, particularly through its data modeling profile.
UMRL. I thought that was mainly for software design.
It was originally, yes, for describing how software components interact and behave. But its remarkable adaptability allows it to be used very effectively for data modeling, too. It provides a standardized way to describe and design database components. It's a common visual language that can bridge different aspects of system design, from user actions all the way to data storage. If we connect UML to what we've learned about ERDs, you can think of database tables in UML mapping to classes and relationships mapping to associations. However, UML extends this with specialized constructs specific to database design, making it quite powerful for this context. For instance, a database schema, which is basically an organizational unit for a collection of tables, is represented as a stereotyped package.
Stereotyped package?
Yeah, it just means we take the general package tool from UML and add a specific label, like schema, to make it crystal clear we're talking about database component. A table itself is a stereotyped class, representing a set of records. And within that table, columns are stereotyped attributes. Here we specify details like data types, string, integer, whether a column can be null, nullability, and if its values must be unique across all records. Keys are explicitly marked in UML. Primary keys get PK and foreign keys get FK right next to the column name. Clearly indicates unique identifiers in how tables relate.
Visual cues again.
It's exactly. Immediately tells a developer or analyst the core structure. UML also lets us model various constraints. These are the rules applied to the database's structure or behavior, helping enforce data integrity and business rules. These can include triggers, stereotyped operations defining activities automatically executed in response to database events, like inserts or updates, ensuring consistent behavior. There's also value verification, marked with check for enforcing specific value ranges, like age between 18 and 65, and uniqueness, ensuring distinct values in a column or combination of columns. This comprehensive set of tools within UML for data modeling is directly relevant to students in BCIS 3389. It helps you utilize standard UML diagrams at the database, class diagram, KO4, and understand how to implement class diagrams from business cases, SO3.
So it helps communicate the design clearly.
Absolutely. These standardized diagrams and notations help you communicate your designs clearly and unambiguously, W1, to both technical teams and business stakeholders. Ensures everyone understands the data blueprint. If we connect this to the bigger picture, this integration of clearly defined business rules, conceptual clarity, and structured modeling tools like UML, this is fundamentally how modern systems analysts build robust, adaptable, reliable digital infrastructures. It's the practical application of theoretical understanding to real-world technology challenges. It ensures that the systems we build aren't just technically sound, but deeply embedded with the intelligence, the operational logic, the policies of the business they serve. This holistic approach ensures not just initial functionality, but also the longevity, adaptability, and ultimate success of systems in our ever-changing digital landscape.
Okay, so we've journeyed from high-level concepts all the way down to the nitty-gritty of physical database design. It's clear there's a huge amount of detail involved, and equally, a huge potential for things to go wrong if it's not done correctly. So, what are the best practices? The essential disciplines for effective data modeling that truly ensure quality and prevent those costly mistakes down the line.
That's a critical question because just knowing the theory isn't enough. Discipline application is absolutely key. Creating effective ERDs and data models isn't just about drawing boxes and lines. It requires unwavering discipline and adherence to best practices to truly ensure the quality and integrity of your data. First, clear naming is paramount. Entities and attributes must be clearly named as nouns, be unique in their context, and crucially be easy for all business stakeholders to understand.
Avoid jargon.
Definitely avoid jargon where possible. Ambiguity here can lead to significant misunderstandings later, even if the model is technically correct. Imagine the confusion if customer in one department meant prospective lead and in another active paying client. Big problems. Second, avoid duplication. Consolidate any duplicate entities in your model. If you find two entities that really represent the exact same business concept, merge them. Maintain a single source of truth for that data. Redundancy wastes storage and is a prime source of data inconsistencies.
Makes sense.
Third, unique identifiers are critical. Every entity needs a primary key that uniquely identifies each instance of that entity. Without a solid primary key, you can't reliably access, update, or manage individual records. It's the unique fingerprint for every piece of information. Fourth, validate relationships rigorously. Ensure your relationships are thoroughly vetted with stakeholders. Make sure they're not repetitive or ambiguous. Each relationship should represent a distinct, meaningful connection. Clearly define cardinality and optionality. Ask, can this exist without the other? Is this truly one-to-many or many-to-many? Finally, and crucially, always uphold data quality from the very first step. As the Snowplow blog highlights, performing upfront validation on event-level data before it lands in the data warehouse is absolutely essential.
Catch bad data early.
Yes. Failing to filter out poor quality data leads to incredibly inefficient resource allocation and, more importantly, bad decisions. Imagine a marketing attribution model fed by messy, incomplete, or duplicated customer data. It could completely misinform your entire marketing spend, leading to wasted millions. Business rules are absolutely key here. They act as intelligent gatekeepers to prevent erroneous, duplicated, or inconsistent data from ever entering your system. These practices are your practical tools for success. They directly impact your ability to implement use case activity and class diagrams from business cases, SO1, SO2, SO3, and ensure higher data quality, which is the foundation for all effective data analysis and ultimately effective business operations and decision-making.
Beyond these essential technical diagrams and methodologies, what's the real-world impact for you, our listeners, as business students on your future careers? How does mastering these data structure requirements set you apart in the job market, whether you become a dedicated systems analyst, a marketing manager, or even a CFO?
The ability to structure system data requirements is a foundational skill that really transcends specific technical roles. It's truly a universal business competency in our digital age.
Not just for the IT folks.
Not at all. It's for anyone who will interact with, rely on, interpret, or manage information systems. This capability directly enables what OWOX-BI calls data-informed decisions. It ensures your systems are truly aligned with organizational needs, preserving critical data quality and integrity. Imagine being in a critical board meeting. A major business decision needs to be made, and you can confidently explain what data is available, how reliable it is, what its limitations are, because you understand its underlying structure.
That's powerful.
That deep understanding gives you immense power and credibility. We see this impact in compelling real-world success stories across various industries. For instance, the fashion retailer reformation used clear data reports built on well-structured data to make agile data-backed decisions about inventory, trends, customer engagement, allow them to react quickly to market shifts. Sauce Company WorkSimpli completely streamlined its operations, saving over 10 hours weekly on admin tasks because they had a robust, well-understood data architecture.
Wow, 10 hours a week.
Yeah, they understood their data, knew what they needed, built systems around that clarity, turned wasted hours into productive ones. PandaDoc, an e-sign sauce brand, effectively closed the loop between its marketing efforts and revenue. They used deep insights from properly structured, integrated data, allowed them to optimize marketing spend and demonstrate clear ROI. This deep dive equips you to demonstrate your understanding of systems analysis and design concepts and ability to communicate these concepts to other people in a written format, W01. It's about more than just drawing a diagram. It's about choosing the right analysis tools, applying them effectively to a business case, and most importantly, communicating your findings and the implications of your data structures clearly, persuasively to a third party.
Whether that's technical teams, business stakeholders, senior leadership.
Exactly. This isn't just theory for your BCIS 3389 course. It's a critical component of lifelong learning for any business professional in our increasingly data-driven world. It's the practical acumen that truly sets you apart.
This raises an important question for you, our listener. How will you use this powerful skill of structuring data requirements? How will you use it to solve problems, drive innovation, and make truly data-informed decisions in your chosen career path? This knowledge isn't just for IT specialists. It's a critical component of lifelong learning for any business professional in our digital age, bridging that gap between raw information and strategic action. So today, we've taken a comprehensive deep dive into structuring system data requirements. We started by understanding why a clear blueprint for data is not just important, but absolutely essential, preventing costly redesigns, project failures down the line. We explored the power of conceptual data models and entity relationship diagrams to visualize core business concepts and their fundamental relationships, creating that shared understanding across an organization. Then, we unpacked the critical, often underestimated role of business rules, from simple definitions to complex derivations, in ensuring both data integrity and precise operational alignment, and crucially, how these rules are enforced at different layers of a system. Finally, we trace the progressive journey from abstract conceptual models through more detailed logical designs and all the way to concrete physical database blueprints, highlighting how powerful tools like UML help us communicate these intricate structures effectively.
Yeah, it's this systematic, detailed, and disciplined approach to truly understanding and modeling data that fundamentally underpins the functionality, the reliability, and the long-term success of every single digital system you interact with daily. From the simplest app tracking your fitness to the most complex enterprise resource planning system at a large corporation, the digital world doesn't run on magic. It runs on meticulously well-designed systems, which are, at their core, built on intelligently structured data.
Thank you for joining us on this deep dive into the invisible architecture of information systems. We truly hope this has given you a fresh perspective and practical insights for your studies and your future career, empowering you to navigate and shape the digital world. If you found this deep dive valuable, please remember to like, subscribe, and share. Your engagement helps us bring more insightful content to you. And don't forget to check the description for additional resources, including materials relevant to your BCIS 3389 course from Tarleton State University's Dr. Sam Pack College of Business.
As you go about your day, maybe think about an app or a system you use frequently. Perhaps your university's registration system, your favorite streaming service, an e-commerce site you like. What hidden business rules, what data constraints, what underlying data structures do you think are powering it behind the scenes, making your experience seamless, or perhaps occasionally frustrating? Consider how those systems were designed from the ground up, starting with their data. Behind every tap, swipe, and click is a system that someone designed. Until next time, keep building the future one process at a time.